Let's discuss the shear surface of a particle, or any surface, and the zeta potential. So imagine we have a solid particle. Okay, so here's solid, and it's got some surface potential. And imagine that it's moving through a solution such that the solution molecules are moving this way and the particle is moving this way. That means there's going to be a shear surface here. What we find is that the shear surface is not exactly at the edge of the particle itself. In other words, we find that if we were to look, there'd be some counterions that would actually move with the particle. So we define this layer here as the shear surface. The shear surface is just the point at which motion begins relative to this surface. So as this particle moves through solution, maybe we have a clay particle that's settling out of muddy water, for instance, that as it sank, or if we had cream that was rising to the surface, and so we had a fat droplet that was rising to the surface within some whole milk to form cream, as it moves up, these particles, any particles here, in this case would be counterions, move with it, and the relative motion is at this surface here. So everything over here is moving down, everything to the left of this dashed line is moving up. So that's a shear surface. Well, what that means is that we have to really rethink where we should start counting our electrostatic potential. If we draw a graph here, we can see that really the thing that's going to be moving is the solid particle plus that attached layer. Okay, we call this the Stern layer. And so we have our surface potential, and then we have a decrease in potential because of the attached ions, the Stern layer. And then we have an exponential k, as we saw in Chapman theory. This potential is called phi delta, the edge of the Stern layer, or the potential decrease to phi delta is caused by that absorbed layer of ions. And the potential at which the shear surface is called the zeta potential. So that's the potential at this dashed line. And the assumption that's often made, and it is an assumption, it's not 100% true, but it's a assumption that's very often made, is that the delta potential, the potential at this kink in this potential curve, is equal to the zeta potential, the potential at the shear surface. And we're actually just going to make this assumption throughout this course. And once we've made that assumption, we can say that the potential out here is going to be based on the zeta potential. It's going to die off exponentially, just like we had before in Chapman theory, except for redefining h as not the distance from the solid edge of the particle, but as the distance from the shear surface. And what we'll find in our section on electrokinetics is it's really easy to measure the zeta potential. So this is something that we can actually measure really easily, and that's going to be, in fact, it's going to become more important to us than the original surface potential.